All right, so here we are back. Now we're working on worksheet number 4. And worksheet number 4 really is a continuation of what we did with worksheet number 3. So if you remember what we did with worksheet number 3, we took a really small peptide, 9 amino acids, and we mapped it onto an alpha helical structure. And we asked questions like, will this adopt an alpha helix? And if so, why? In other words, we were looking at the things that stabilize that alpha helical structure, and we looked at the fact that there can be these side chain interactions that can either disrupt or stabilize the hydrogen bonds that are forming between the backbone, allowing either the alpha helix to form or not. Okay, and we talked about the stability of them at different pHs and in different mutations. Okay, so now what we want to do is we want to go much larger. Okay, in that, and we're still thinking about our primary objectives in the class to, first of all, recognize structural features of a protein, and then secondly, understand what forces, okay, or what interactions will stabilize a protein structure, okay? And we're going to do that by comparing two different proteins that have the same size of primary structure, okay? So I have protein number 1 and protein number 2, and there's a description here in this table of the primary structure, secondary structure, and tertiary structure. And the primary structure, you'll notice, has both of them have 382 residues. So these are the same size proteins, okay? They don't have quaternary structure. They're only one subunit, okay? And then there's some differences that are described here, and we're going to be answering questions that are found on worksheet number 4. So once again, I will encourage you to go ahead and pause it and go through those questions. There's 4 of them, okay? What will the sign on delta S be for a globular protein, and why? What would happen to this if the solvent were changed to benzene rather than water? And then number 2, what will the sign on delta H be for our 2 hypothetical proteins? Would the delta H be different for the 2? State an argument for why you would answer the way you did. And then which protein has a larger TM and which protein has a deeper folding funnel? Draw a hypothetical folding funnel for each protein. Okay, so pause it, work through those things, come back and listen to my explanation of it. Now, before I do that, real quick, by the way, I want to say that you'll see in the primary structures these things, disulfide bonds listed, okay? Disulfide bonds are technically listed as a primary structure, okay? And the reason that is the case is because they're covalent bonds that hold amino acids together in a protein, and that's our definition of a primary structure. However, those covalent bonds, disulfide bonds, these are between 2 cysteine residues, don't form until really the tertiary structure forms. They're what would be considered long-range interactions, okay? So just keep that in mind as we move forward, okay? All right, so go for it and then come back and listen to the rest of this. Okay, so I trust that you've done the questions, and now what we want to do is start to answer some of those questions. And the first one is, what will the sign on delta S be for the globular protein, and why? Okay, so hopefully you have some answer in your mind about this, and this comes down to this statement on our table. Each of these will have a well-formed hydrophobic core. Okay, now understand that we want to compare these 2 proteins one to another in terms of their stability at the end of this, so we got to keep all these things in mind. All right, but they both have well-formed hydrophilic cores. Now, when we think about the delta S and ultimately the entire protein, okay, and its stability, first of all, I guess I said when we think about delta S, let's first of all think about the thermodynamics of the entire protein. Okay, so the entire protein, from a folding standpoint, okay, is going to be delta G is equal to delta H minus T delta S. Okay, so the stability of our protein is dependent upon the magnitude and sign on delta S and the magnitude and the sign on delta H. Okay, all right, and so in the first question, it's asking about this delta S. What is the sign on delta S? Okay, and so what we're going to think about here with this delta S, we want to recognize, okay, as being really what we'd be considering delta S total, which would be essentially this, okay, is equal to the change in the S of our solvent or water, okay, plus the change in the S of our protein, or what we call conformational delta S, okay, meaning the change in the entropy as the protein folds and think about only the protein. And then we have change in the entropy of the solvent as the protein folds, but only the solvent, okay? And so what we want to do, first of all, is just think about this, right? And let me just ask you, okay, is that going to be positive or negative, right? When the protein folds, going from its unfolded state to its folded state, will this be positive, or will this be negative, or will it be at zero? What do you think? And hopefully you thought to yourself, this should be negative, okay? And the reason that it should be negative is because we're going from the unfolded state, and the conformational landscape of the unfolded state is really large, meaning that there are truly almost an infinite number of or an astronomically large number of conformations that can be in the unfolded state. I guess it's not truly infinite, but it is very, very large. There's lots of degrees of freedom within the unfolded state of the protein, okay? However, as the protein folds, it's going to adopt really a very, very small family of structures that are all very, very similar to one another, okay? And we, to the point where we can say essentially in this class, there's really one folded state, okay, and one conformation within that. So we're going from this huge degrees of freedom to very small degrees of freedom, and that means that this is going to be negative or decreasing entropy in the protein, okay? Now, at the same time, okay, delta S of the solvent, well, this is going to be much different, okay, thing to think about. In the unfolded state, all the hydrophobic side chains are exposed to the water, okay, meaning that water has to interact with them, and the water molecules that are interacting with the unfolded, with the unfolded protein, but in particular the hydrophobic side chains are going to adopt these clathrate cages, right? So that's a very ordered and structured form of water, okay? However, as the protein starts to fold, those hydrophobic side chains start to go into the core of the protein, and the water is stripped off, and the water goes back into normal solvent properties of water, okay, very disordered. And so we have this fairly massive increase in entropy of the solvent, going from all those cages that are wrapped around the hydrophobic side chains to being taken off of those, coming out of their cages, and therefore we have this very positive value. And so we can say that this in water, okay, is positive. Okay, I was thinking about water, by the way, as my solvent. Right now, the question then is, okay, well, what will delta S be? We have positive and we have negative. Well, that would depend on the magnitude of these two things, and it turns out you can make a really solid argument for the fact that this will be positive. Okay, and the reason that it will be positive is because there's more solvent than there is solute. Okay, the protein's solute, okay, and the water is solvent, and there's just more of those molecules, and so there's a bigger increase in entropy than there is a decrease in entropy, and so that's going to add up to be positive. Okay, now the question goes on to say this, well, what if it was benzene, right? Instead of water, what if it was benzene? And obviously in that case, things are going to change. In benzene, this solvent, delta S is going to really be nothing. It probably wouldn't be positive or negative. It would probably be zero. There's not going to be a real change in the solvent, and therefore the delta S of the protein is going to be negative in that case. Okay, and the protein won't fold actually in that case. Okay, because of the importance of the formation of the hydrophobic core. Okay, now the next question is this, and that is, well, what about the enthalpy of the protein? Okay, and remember, we have now dealt with this, and we're going to think about this in biologically relevant terms. We've said that this would be positive, so now we need to go to delta H. Okay, and with delta H, we need to get a new board here, and we want to always think about delta H in terms of bonds formation and bond breaking. Okay, in fact, delta H is going to be equal to the enthalpy of the bonds broken, so I'll just put BB, minus the enthalpy of the bonds formed, BF. Okay? Now, when we consider a protein folding event, going from an unfolded state to its folded state, okay, we want to think about the types of bonds that have to be broken in that process. Now, let me ask you this question. Are there bonds broken as the protein folds? And if there are, what are those bonds? So think to yourself, what's the answer to that question? Are there bonds broken? And if there are, what types of bonds are broken? And hopefully you first of all came up with yes, bonds are broken. And the types of bonds that are going to be broken are going to be hydrogen bonds and ionic bonds. And some of you are saying, yes. Why in the world are those broken? Okay. And the reason is because the protein is going to have to interact with the solvent. Okay, so in the unfolded state, the solvent typically is going to be water, and in that water there's going to be ions. Sodium and chloride are the two most common ions that you find in a biologically relevant solvent. Okay, and sodium has a positive charge, chloride has a negative charge. Well, those water molecules, as well as the negatively charged chloride and the positively charged sodium, are going to interact with the protein. Okay, water is going to form hydrogen bonds to polar side chains and the backbone, and the negatively charged chloride is going to interact with positively charged side chains, and the positively charged sodium is going to interact with negatively charged side chains. Okay, and so those are ionic bonds and hydrogen bonds that are formed between the unfolded protein and the solvent. Okay, and the ions in the solvent. Well, those things have to be broken for the protein to fold. Okay, in other words, all the water has to be stripped off of it as the protein folds up. Okay, and so you're going to break those. Now, the next question is, well, what types of bonds are going to be formed? Of course, bonds are going to be formed. Okay, and so what types of bonds are going to be formed? So go ahead and answer that question, and then come back and listen. Okay, so hopefully you figured this out, and you realized, okay, well, hydrogen bonds are going to form. In fact, when we think about secondary structures, we know that backbone hydrogen bonds are going to stabilize alpha helical structure and beta sheet structures, okay, which are of course part of the structure. Okay, ionic bonds, long range interactions are going to form. Okay, so these would be ionic bonds between, like, say, a lysine and a glutamate. Okay, that are close enough in proximity to each other to form that ionic bond. Okay, now if we were to leave it at just this, okay, and we were to think about, well, what would our change in H be for protein folding, then it would be reasonable for us to say that, well, the change in H of protein folding is going to be 0 or debatable. Okay, because you're breaking the same types of bonds that you're reforming in the folded state. And so it's reasonable to think that the strength of the hydrogen bonds and the ionic bonds are going to be the same, and the numbers of the ionic bonds and hydrogen bonds are going to be about the same, so it's going to be about 0. Okay, and so this is a debatable quantity. However, there are things that can tip this delta H into the negative direction. Okay, so if we come back up here, there are two things that we want to look at here. First of all, there are these things, disulfide bonds. Okay, we'll highlight this in protein number 1 and number 2. Well, disulfide bonds are covalent bonds. Okay, and so those can form in a protein structure, but they're not something that are found in the bonds broken value. Cysteine side chains don't form disulfide bonds to anything in the surrounding biological solvent. Okay, so when they form, we only have a contribution to the bonds formed value and not the bonds broken value. Okay, because so that can then tip delta H in the negative direction because it's going to make bonds formed quite a bit larger. The second thing that we need to look at here is salt bridges. Buried salt bridges or buried ionic bonds. Okay, and so what we can do here is this. We can say that buried ionic bonds can form in this, but you don't have buried ionic bonds in the unfolded state. And you think, well, what is the buried ionic bond and why do we care? A buried ionic bond is a bond that is buried in the hydrophobic core. Of course, the hydrophobic core can't form until the protein is folded. Okay, And these are ionic bonds that are found in a hydrophobic environment. Well, ionic bonds found in a hydrophobic environment are stronger than those found in the hydrophilic environment. Okay, in fact, when we think about it this way, okay, coming back to, I think it was chapter 2, we talked about the energy of attraction between two ions is equal to Q1 and Q2 and a proton charge. Okay, don't worry about that too much. And then D times L. Okay, and the important factor of this is going to be the D, the dielectric constant. And the dielectric constant, if you remember from chapter 2, okay, is going to be about 80 in water, and it's going to be about 4 in the hydrophobic core. All right, and the big thing here is the difference in magnitude, 80 and 4. That's a 20 times difference. And you'll notice that this is in the denominator, so the smaller that number becomes, the greater of energy of attraction between the two ions. Okay, well, these ionic bonds up here, right, they're all surrounded by water, so the D of these is going to be 80. Whereas in this case, right, and we could say the same thing here, D of these is 80, because they're just ionic bonds that are forming, but the D of some of these, which are found only in the folded structure, is going to be about 4. And those ionic bonds are about 20 times stronger than the ionic bonds that were broken to form them. Okay, so they're stronger bonds. Okay, and so that can then cause bond formation, or the enthalpy of bond formation, to be a larger value, and that can tip the enthalpy in the negative direction. Okay, all right, so those two factors, those covalent bonds, the disulfide bonds, and the baried salt bridges are going to be, or baried ionic bonds are going to be things that can tip that H of bonds formed. They can make it larger, and that will tip delta H of folding into the negative direction. Okay, now the question then, we go on and say this, okay, it says this: would the delta H be different for the two proteins? State an argument for why you answered that the way you did. Well, let's come back up here, okay. Look at protein number 1 and number 2 here. Okay, protein number 1 has disulfide bonds, protein number 2 doesn't. Protein number 1 has 9 baried salt bridges, and there's only 4 baried salt bridges in protein number 2, right? And that means that this, okay, protein number 1 is going to have a much larger bond formed value than protein number 2. They probably both have the same bonds broken value. Okay, and because it's much larger bonds formed, then we're going to say that the delta H of protein number 1 is going to be more negative than protein number 2. I would say that they're both probably negative because the baried salt bridges in both of them. But protein number 1 has more baried salt bridges, and it has those 6 disulfide bonds, making it more negative. Okay, all right. Now, that can then move us to, well, which protein has a larger TM? Well, what is TM, if you remember? TM remembers the melting temperature of the protein, okay? And the melting temperature of a protein, okay, is related to stability. The higher the melting temperature of a protein, the more stable that particular protein is going to be, okay? And so when we look at this protein number 1, okay, and we're saying this, we could go here, delta H, okay, of number 1 is more negative than 2. I should put number 1, there we go, then number 2. Because of that, then, we can say that the delta G of folding for protein number 1 is going to be more negative, because it has a more negative delta H value. That's going to contribute to more negative delta G value, and that's going to make protein number 1 more stable, and that makes then its TM larger. Okay, so which protein has a larger TM? Protein number 1 does. Okay, now it says, well, which protein has a deeper folding funnel, and then draw a hypothetical folding funnel. Well, let's go ahead and do that. So number 1, okay, is going to look like something like this, and I'll just draw a very simple folding funnel. Okay, and protein number 2 is going to look something a little bit more shallow. Okay, now remember, a folding funnel, the rim of the funnel represents the unfolded state. And then as we get down to here, this would be the native state, okay? And the depth here that we've got here, we're essentially plotting out G values, okay? So this depth here, going from here to there, is going to be negative delta G, okay? And it's going to be a larger magnitude of a negative delta G than this one. This will be negative delta G as well, but this one's larger in magnitude. Deeper folding funnel, meaning this, that the protein takes more energy. It takes more energy to get the protein out of the native state back into the unfolded state than it does here, okay? Meaning that if you're going to melt this, it would take a higher temperature to melt it than protein number 2, okay? Now, let's do some application here. There are these organisms that live in the Yellowstone hot springs, right? Or very extreme temperatures, what we call extremophiles, okay? And they can live at near boiling temperatures. Like they thrive at near boiling temperatures. Okay, what's interesting about those organisms is that means that their proteins, every single one of them has a TM that is greater than boiling temperature, right? TMs of greater than 100 degrees Celsius. Well, you and I's protein in our cells, I mean, TMs are generally speaking somewhere around just above body temperature, about 40 to 45 degrees Celsius. Some are more stable than that, but that's about right. Meaning that at boiling temperatures can be very dangerous for us, obviously. Extraordinarily dangerous because it will unfold all of our proteins, not to mention just burn the heck out of us, okay? So the question is, well, what's the difference between those proteins and those thermophiles versus our proteins? What makes those more stable? And as we've investigated those, okay, and sometimes it's kind of like comparing apples to oranges because we can't get the exact primary structures comparison because the primary structures are different, but still we can look at them and on average those proteins have more ionic bonds, particularly more buried ionic bonds, and also more disulfide bridges, okay, meaning that their enthalpy of folding, their bonds form value is much greater than the bonds form value that we have for our proteins, okay, and that makes them more stable and higher TMs. All right, so hopefully you found this extraordinarily helpful. Okay, if you have, again, questions, please let me know.